Okay, we're going to talk about the first derivative test. First, we need to talk about something called the increasing and decreasing test. And I'm going to kind of lump these two things together. They're all part of something greater that we're going to do later on when it comes to curve sketching. But if we look at a function and we take the derivative of that function, where that derivative is positive, if it's bigger than 0, the actual function itself is increasing over that interval. If the derivative is negative, then the function is decreasing on that interval. So to figure out where a function is increasing and decreasing, I'm going to simply take the derivative and find where it's positive and where it's negative. Okay. First step, take the derivative. F prime of x would be 12x to the third minus 12x squared minus 24x. And then if I want to know where it's positive and where it's negative, I first want to figure out where it's 0. Right? So the next thing I'm going to do is I'm actually going to set this equal to 0. And I'm going to find the places where the derivative is 0. So that's going to require us to factor out a 12x. We would have x squared minus x minus 2. I'm going to continue to factor. That would be x minus 2 and x plus 1. And then if I set those each equal to 0, I'm going to get x equals 0, x equals 2, and x equals negative 1. Okay, now with those numbers, I'm going to then make a number line. I'm going to put those in order, negative 1, 0, and 2. Now, since those are the places where the graph is 0, in each interval between those zeros, we're going to have a function that's either positive or negative. So what I'm going to do is I'm going to take a number in each one of these intervals, something smaller than negative 1, something between negative 1 and 0, something between 0 and 2, and something greater than 2, and I'm going to plug those into the derivative to see if I get a positive or negative value. I'm going to look at my most factored form of my derivative. So if I plug in a number less than negative 1, like negative 2, this 12x, if I plugged in negative 2, would give me a negative value. Negative 2 minus 2 would also give me a negative value. And negative 2 plus 1 would again give me a negative value. So I would have a negative times a negative times a negative, which would be negative. Okay, so it's going to be negative there. If I plug in a number between negative 1 and 0, like negative 1/2, the 12x would give me negative. Negative 1/2 minus 2, that's still negative. Negative 1/2 plus 1 is now positive. And a negative times a negative times a positive is a positive value. Between 0 and 2, like 1, 12 times 1 is positive. 1 minus 2 is negative. 1 plus 1 is positive. A positive times a positive is going to give me a negative value. And something bigger than 2, like 3, I would get a positive for all 3 of these. So that's going to give me a positive value there. Okay, now again, what does that tell me? That tells me that my graph is decreasing in this interval, increasing in this interval, decreasing in this interval, and increasing in this interval. So where is it increasing? It's increasing from negative 1 to 0 and from 2 to infinity. Where is it decreasing? It's decreasing from negative infinity to negative 1 and from 0 to 2. Now keep this in mind because I'm going to copy this down here below when we start to look at the first derivative test. So that's the increasing and decreasing test, but then you use that to do the first derivative test, and that says that if c is a critical number of a continuous function. So how do we find critical numbers? We set the derivative equal to 0, or we find where the derivative is undefined. Now, if we're dealing with polynomials, I don't have to worry about that second part. I'm just going to find where the derivative is 0, and those are going to be critical numbers. So I actually have those critical numbers here. Those are the 0, the 2, and the -1. Those are my critical numbers. If the derivative changes from a positive to a negative at a critical number, then there's a local maximum there. So what that means is, if I go from increasing, right, a positive value, to a negative value, I'm going from increasing to decreasing. If I'm going from increasing to decreasing, then there's going to be a local max there, right? We're going to have to hit a highest point before we start going down. Now again, this is we have to make sure that the assumption is that it's a continuous function. Conversely, if f prime goes from a negative to a positive, then we're going to have a local minimum. So at -1 here, I'll go from a negative to a positive. I'm going to have a local minimum there. And then if f prime does not change sign at c, then there's going to be no local max or local min there. So if I had a couple of increasings in a row, I can't say if I go from increasing to increasing that I'm going to have a local max or a local min there. Right? That's not going to happen. So this is the same function as above. I'm going to copy down that chart that we had. So we had -1, 0, and 2, and we had that here it was negative, so our graph was decreasing. Here it was positive, so our graph was increasing. Negative here and positive here. So it looked like that. So what that means is that there is a local minimum at -1. I'm going from decreasing to increasing, which means we're going to have a local minimum there. And there's also going to be a local minimum at 2. Right? So I'm going from decreasing to increasing at 2, so there's a local minimum there as well. Now, I'm going to write those as coordinate points. I want to find what the actual local max or local min coordinate point is, and so I need to find that y value, but I'll get to that in just a second. And then we have a local maximum at 0. Right, because I go from increasing to decreasing at 0, so there's a local max there. Okay. Anytime that you need to go back and find a y coordinate, you do not plug these numbers into the derivative. If you plugged them into the derivative, you would get 0 for all of these. Why would you get 0 for all of those? You got 0, you got those numbers by setting the derivative equal to 0, right? You were finding your critical numbers, so you set the derivative equal to 0, and we got 0, 2, and -1. So therefore, if I plug in 0, 2, and -1 into the derivative, I would just get 0 for all of these. And that's not correct, right? So what we want to do is to find the actual coordinate point. I'm going to take each of these x coordinates and plug them into my original function. If I plug them into my original function, I can get the y values there of my local max and local mins. 0 is easy. If I plug in 0, I get 5. So that tells me there's going to be a local maximum at 0, 5. If you plug in -1 into this function, plugging in -1 would give you 0. And if you plug in 2, plugging in 2 gives you -27. Okay, so there should be local minimums at -1, 0, 2, -27, and there's a local maximum at 0, 5. Now, the idea here is that we can figure out things about the graph of this function without actually looking at the graph. But I am going to go to Desmos really quickly just to show you what we have found and verify that it is correct. So I have my function here, and what we found is that at -1, 0, there is a local minimum. At 0, 5, there is a local maximum. And at 2, -27, there again is a local minimum. Now, if I just think about increasing and decreasing, the graph is decreasing. We're always reading from left to right. The graph is decreasing from -infinity until we get to -1. It increases from -1 to 0. It decreases from 0 to 2. And it increases again from 2 to infinity. So everything that we found here is shown in that graph. I can see where it's decreasing and where it's increasing. I can see the coordinate points of my local maximum and local minimum. But I get that all through the derivative of the first derivative of the original function.